our DLL from yesterday. Okay, now we're going to graph negative 3x squared. A few things that we want to talk about very briefly that we didn't talk about yesterday. When we graph a linear equation, basically everything we've done so far this year, how many points are we typically trying to find? 2. Because we know if we're dealing with a straight line, that I can find 2 points, my line is good. Now that we're dealing with something that's not a straight line, how many points do you think you're going to want to find? Like 4. Probably more than 2. The only reason I say that, if I were graphing here y equals x squared, right, that's the parent function we talked about yesterday. I know that if x is 0, y is 0. I also know that if x is 3, y is 9. The problem there, I can make that a straight line. Right, I could just graph it like this. Right, it's a little deceiving if I only utilize 2 coordinates because that graph actually is a curved line. If I added more coordinates to it, if x is 2, y would be 4. And if x is 1, y would be 1. So I can see that curve only after I have multiple points. So keep that in mind. On some of your papers, I did write, just add more coordinates. You did it right, you just needed to add a couple more coordinates. Now, looking at y equals negative 3x squared, yesterday we talked about a few things with that coefficient. What do I know about the graph? It's going to go down. How do I know it's going to go down? Because the 3 is a negative. Good. Is it going to be like really wide or is it going to be a little skinnier? Really fat or skinnier? Well, let's graph it and let's find out. If I'm going to graph a quadratic, I can use the table. Okay. Some of us need to recall when we substitute values in, what operations are done first. If I substituted in a value of 0, 1, 2, and 3, if x is 0, what's y? 0, because 0 squared is 0, and 0 times negative 3 is still 0. Good. The order of operations there, the exponent is first. You have to square the number first. Some of you are not doing that. If x is 1, what is y? A negative.
It's a positive. Wait. Oh, wait.
Negative 3. 1 squared is 1. 1 times negative 3 is negative 3. If x is 2, negative 12. 2 squared is 4. You are squaring the number first. 4 times negative 3 is negative 12. If I wanted to do 3, I could. Negative 27. Again, 3 squared is 9. 9 times negative 3 is negative 27. This is what's making the line go down. If you don't multiply by that negative 3, your coordinates are going to be in the first quadrant here. So if I graph this, 0, 0, 1, negative 3, 2, negative 12 is actually off my graph here. You could also do negative 1. If x was negative 1, what's y?
Negative 3.
Negative 3. Negative 1 squared is 1 times negative 3 is negative 3. So my graph would look like that. Before you even start graphing, just look at the equation. You should be able to figure some things out. Some of you had graphs that look like this. There's no reason to have something going up. The negative 3 alone tells you that it should go down. Plus, if you plug the values in, if you made a little calculation error and all of those ended up being positive, just looking at the equation should give you a little bit of insight into that. Right? And that's actually what we're talking about today. We're going to continue to talk about what we identified in that first term, and now we're going to talk about other parts of the quadratic equation and what they do to the graph. Okay? So if I needed to place these in order from largest to smallest, which graph matches which? So we have the function of x equals negative 4x squared, function of x equals 1/4 x squared, and then the function of x equals x squared. Jordan, give me one.
The first one goes with the first one?
Yeah, the first one actually goes here. Now, there's a few reasons we know that. First, what do we know about the negative 4x squared?
That means going
The graph's going to go down. Notice the thickness of the parabola. Is it really wide or is it really skinny?
Skinny.
Why skinny?
Because the coefficient is bigger.
Yeah, our coefficient is bigger, which means as we multiply, you're actually multiplying by a larger number. It's going to move faster. Okay, Jocelyn.
The second one goes to the second.
Yeah, the second, I think at some point I had these in a different order, to be honest. Because this morning I was like, wow, I didn't even make them work for it. They were in order. Notice the difference between the 1/4 x squared and the -4x squared. Even if that -4 was positive and it was going up, notice the difference in the width of the parabola. Think about just the number 10, right? If I had the number 10 and I multiplied it by 4, that would be 40. That's a big jump. But if I multiply 10 by 1/4, that's 2.5. That's very small. So that's what's making it wider. It's actually not growing at as fast of a rate. And then here we have our parent function of y equals x squared.
Aaron?
The parent function, that just means like the most basic quadratic function. So now we're going to talk about linear. Back to linear. So far today, well, so far in this unit, we have this quadratic, sorry. This is our basic quadratic function here. We have y equals ax squared plus bx plus c. So far, yesterday, we focused on this term, this ax squared. And we learned a few things. First, that exponent is going to make our line curve. That's why we're dealing with a parabola and not just a straight line. Second, this a value indicates if our line is going up or down, like if our parabola is opening up or down. Also, if it's skinny or fat. That's what we talked about yesterday. Today, we're going to talk about this c value, what this does to our graph. Okay, so that's what we're going to focus on today. So let's think back to just the beginning of the year. If I was graphing y equals x plus 3 and y equals x, how would I graph y equals x? It'd be a straight line. It would go through the origin. Good, so I'll plot that point. What's another point on that line, y equals x? Just so I can draw the line.
1, 1.
Yeah, if x is 1, y is 1. Good, I have that. How about y equals x plus 3? Can you give me coordinates on that line? What do you mean positive 3? Yeah, our y-intercept is at positive 3. What else? You can write 1 and run 1. So here we go. 6. Oh, that's supposed to be red. For dramatic effect, it would have looked really nice. How are they the same? Wow, my line's not that great. They're parallel. What does that mean?
Now it's red.
They will never touch. Why not?
Because they have the same slope.
They have the same slope. Okay, good. Those lines are parallel, even though my drawing's a little off. They are parallel. How in the equation do I know they're parallel?
The slope.
The slope. Here. I only have a positive x here. What's different?
The y-intercept.
The y-intercept. So in terms of the lines, what did I do to really go from one line to the other? Yeah, so even though it's the same line, it crosses the y-axis at a different point. So we're going to use this same understanding to figure out the differences between this equation, y equals ax squared plus c, and y equals ax squared. So how would the graph of y equals 2x squared plus 3 be different than the graph of y equals 2x squared? Now, I want you to work on filling in this table right now because this is a weakness. Right? Some of us are forgetting how to multiply. I know that sounds silly because we've been doing it for so long, but how would you fill in this table? Everyone's pencil should be in their hand. You should be filling in this table. I know daylight savings time is really hurting us. We got to stay awake. If I substitute in, you don't have to go in any order here, -2, -1, 0, 1, 2. They don't have to be big numbers, right? Just to get an idea of the curve of the line. Remember that exponent first, our order of operations, we square the number first, then we multiply by the coefficient. Who wants to help me out with the y equals 2x squared? I know you're just starting to multiply them, but as we go through. If x is 0, y is what? It would be 0. Good. If x is 1, What would y be? 2. What about if x is 2? It would be 8. 2 squared is 4, and then 4 times 2 is 8. Can anyone do negative 2? What's your sign?
Positive.
Is it a positive 8 or a negative 8?
Positive.
Why positive?
Because.
Yeah, if I negative 2 squared would give me positive 4, and then 4 times 2 would be 8. So that means negative 1 would give me what value?
Positive 2.
Positive 2. How about the other line? Y equals 2x squared plus 3. If x is 0, 3. This would give me a value of 0, but then I'm adding 3. How about if x is 1? 5. If x is 2? 11. You're seeing the pattern. How would the graph look different? What's wrong? Substituting in the numbers? All we're doing is substituting in a number. We didn't do anything yet. So we just chose any x value. And when we graph, sometimes that gets to be the challenge. Like, how do I know what x value? You can choose any x value you want. The reason why we typically start with smaller is because if you're dealing with any type of multiplication or squaring or anything, you'd rather deal with 0, 1, 2. Start there and kind of see what calculations you would come up with from there. So if I substitute in for x, I decide the x value, and then I'm going to calculate the y value. So here, if we use these x values, this is our y value for this graph. And then this would be the y value for the other graph. Those are the coordinates. If I graph this first column here, y equals 2x squared, I'm going to use the coordinate negative 2, 8. I'm also going to use negative 1, 2, 0, 0, 1, 2, and 2, 8. I'm going to use those coordinates, and that's going to form my parabola. All right, I'll do the same thing with the other column, and it's going to look something like this. So if I have my two columns, we start there with the table to find any coordinates we can. And again, you want more than 2. You don't need to do 5. 3 is enough. You'll see the curve. Which line is which color? Take a look first. Which line is y equals 2x squared? Is it red or blue?
Red.
It's red. How do you know it's red? So be careful saying it starts at 0 because it doesn't. Right? That line doesn't have a start. I know what you're thinking because like if you were to draw it, you'd probably start there and then go that way and then that way. But this quadratic doesn't have a beginning, right? It goes on forever. That 0, 0 is a point though. What do we call that? That coordinate is the vertex. It's the lowest point of the graph. So that means the other line, the blue, is y equals 2x squared plus 3. How are those lines different? Oh, so they have a different, their vertex is different, where you can see that they have a different minimum. How else are they different? Different, did you say different shape? How else are they different? They have a different vertex. That's a good one. Are the parabolas different?
Yes.
Yes or no?
Well, I can't see, so.
Do they look different? The parabolas. Do we know for certain that they're not different?
Maybe if we like stretched out the blue ones, they're probably the same size.
Okay. Well, let's. So,
Well, if we were able to tell what if a line was whatever by the slope,
so if that was my.
what could we use in the equation to know if the parabola is the same or different?
That's actually a good question. Can you restate that? Because the way you worded it is probably better than what I would have asked. Say it again.
Um,
Do you remember what you just asked?
I said, well, we were able to use the equation to find out if the lines were parallel. What could we use in the equation to find out if the parabola were the same?
Good. In the example that we started with when we went back to linear, that y equals x and y equals x plus 3, we knew that they were the same line because of the slope, that x. Right? What here would indicate that the parabolas would be the same shape? The 2x squared. Right? They're going to grow at the same rate. So that's still, the way that our parabola is going to grow is still dictated by that number. And in both of them, it's 2. It's positive 2. So no matter what I calculate, I'm always going to square it and multiply by 2. What's different about them? Why do they look different?
The plus 3.
Yeah, the plus 3. What did we do from one to the other? We just moved it up. How many units? Yeah, we moved it up 3 units. This represents the same thing as our y-intercept. So I just want you to write this down. The graph, you don't have to write the whole thing, just what's in red. The graph of y equals 2x squared plus 3 has the same shape as y equals 2x squared, but it's just moved up, right? You can see that it's just kind of shifted. It does appear in the image that the red parabola is wider, but it's not. You're only seeing the very base of the blue one. If you showed the whole thing drawn, it would be the exact same thing. The reason we know that ax squared term, the first term of the quadratic, is what determines the shape and direction. So if they're the same, then they have to be the same shape and direction. But similar to a linear equation, that c value is going to move our line up and down. So that's what's going to move it. If it was positive, it would shift it up. If it's negative, it's going to shift it down. That represents your y-intercept. Right now, that is on the axis of symmetry. It will not always be. What I mean by that is eventually you're going to have a graph like this. That 2 would still be like plus 2. Like it would still that would still represent your y-intercept. And we'll get there in a while. So if you had this entire, actually, yeah. So we know that this term determines if it was skinny or fat, if it was up or down. This term moves the entire thing, moves the entire parabola up or down. Tomorrow and towards the end of the week, we'll talk about what that middle term does. It does some crazy stuff.
No.
It's the middle term you gotta watch out for.
It makes
Go all around. Yep, you're right.
I guess.
Well, I mean, really, if you think about the only other thing that could change with the quadratic would be that, and that's what the middle term is going to do. Okay, is that right? Okay, so let's use a real scenario here. So even though we've been graphing quadratics, we're going to utilize a real scenario to see the limitations. Because if you have to answer an actual problem, there's certain parts of your quadratic you're not going to use. So here we have an acorn. It drops from a tree branch 20 feet above the ground. This function here represents the height of the acorn after t seconds. So we're going to graph this, and we're going to figure out the answer, the solution. When is the acorn going to be on the ground? Just looking at the equation, what do we know it's going to look like? What do I know about the graph?
Yeah.
It's going to go down. What kind of line is it going to be? It's going to be a parabola. It's not going to be a straight line. Or how do I know it's not a straight line? Because the exponent. Good. So the exponent tells me that it's going to be curved. What tells me it's going down? The negative. How fast is it going down?
Very.
Yeah, it's going to go pretty fast. It's going to be skinny. It's not going to be fat. And then what else do I know about the parabola?
It has a y-intercept.
Yeah, it has a y-intercept of 20, so it's going to be shifted up above the x-axis, up top, about 20 units. Okay, so we can actually come up with some values. Is it possible for the acorn's height to be a negative number?
No.
No. Okay, so keep that in mind as we're talking about limitations to what the quadratic would look like. Okay. So here, we already know the function for the acorn's height. We also know that it started at 20 feet high. Right? Imagine if you just like dropped an acorn out of a tree. I don't know why we would do that, but let's just pretend. So what we need to know the graph, and we want to try to identify when it hits the ground. we're going to use a table, we'll calculate, but we're gonna estimate this, okay? We're not gonna come up with an exact, we don't have graphing calculators or anything like that, so we're just going to focus on how to identify on the graph where this location would be. What values could I put on my graph
What is that?
for time? This is our table, and then this is gonna be our graph.
Oh.
Alright, okay, so if at t is 0, at 0 seconds, where's the acorn? 20. So I can do this. Okay. 1 second?
24, 30.
At 1 second, where's the acorn?
4? No, that's
2 hours.
no wait. 4 plus 1.
Wait,
What are we talking about?
positive 4.
Oh.
How do you know positive 4, Ibrahim?
Because you're multiplying a positive.
But we didn't distinguish.
I mean, no, a negative and a negative. To get.
Oh, where am I multiplying negative and the negative?
Wait.
We'll just talk about what you're substituting in. You're squaring 1, which is 1. You're multiplying by negative 16, so you're going to calculate negative 16 plus 20, and which is 4.
Oh.
What if I had 2 seconds?
Negative 48.
What do you think, David? Negative. Is it? It's definitely a negative. Check your calculation. Negative 44. 2 squared is 4. 4 times negative 16 is negative 64. And negative 64 plus 20 is negative 44. So where does, just looking at the table, where's this acorn going to hit the ground? Between where? Somewhere between 1 and 2 seconds. Because at 2 seconds, it's below the x-axis. So here, if I have when x is 1, y is 4, and then when x is 2, y is like way down there, it's going to look something like that. So if I had to just graph the parabola, it would look something like that. Right? But for the context of this problem, what parts of the parabola do I not even need to consider? Which, where?
Below the x-axis.
Okay, so anything below the x-axis doesn't matter. Why doesn't anything below the x-axis matter here?
Because you can't have
So I'm not going to have negative feet. And the reason I'm not going to have negative feet here, the ground is the x-axis. If we had something like that, it could go below the ground, then maybe. But
Like
for
a
this
drill?
problem, yeah, like if you drilled something below the ground, sure. But for this, the ground is x, the x-axis. What else don't I need here? What else on this graph do I not need?
The left side.
I don't need the left side. Why not? What does the left side of this graph represent? Negative time. And I don't,
So you
there's
can't have
no
negative
such thing. So in terms of context, this is really all I need. Right. So even though we have an entire parabola, sometimes you're not going to need the whole thing.
So what's that called?
It's still the graph of the quadratic. I'm just erasing the other parts of the parabola because we don't need
So
them.
that has no name. One's just
We can name it
We should
if
name
you'd like to.
Half the parabola.
The parabola portion.
parabolic line.
The things we come up with here. Okay, so this acorn hits the ground when its height is right at 0. You can see where this is. What about what? What is that approximately? 1.3? Okay, maybe like 1 point, maybe a little bit closer to 1. How can I find it exactly? Like what equation? Oh wait, let me go back here. We're going to talk about the equation in a second. This question always tends to get wrong. Is the speed of the acorn greater at this point or at this point? At 0.25 seconds or at 0.75 seconds? Where is it faster? Think about what it means to be fast. What part of the graph represents an increase in speed? when a line moves faster, what do we know about it? It gets, okay, skinnier, but how does it move? It's steeper. So at which point, are we steeper here or are we steeper here?
The first one.
No,
Oh wait, no, the second one.
Yeah, we're actually steeper later at 0.75, and it's probably a little bit easier to see if I compared something like 0.25 seconds to here at 1.5 seconds. You can see that here, if you had to draw that line off of it, it's not really moving that steep, but then it really starts to speed up. Right? So you'll see questions like that just try to get you to identify the movement on the quadratic. It's not constant, right? And we've been talking about constant and linear relationships all year. Now we're transitioning to things that will change over time, whether they get faster or slower, and that's where the curve of the line comes in. So as you're answering those questions, just think all about the curve of the line and how it applies. So what equation could we use if we wanted to figure out exactly where the acorn hit the ground? We already have the equation of the graph. How could we use that to actually solve and find out how long it took the acorn to hit the ground? Zara, what do you think?
maybe the height is 0.
Yes, I can use the same function, h equals negative 16t squared plus 20. And what would I do? I'd substitute in, like Zara just said, 0 for the height, and how would I solve? Well, I'm trying to find the time.
Subtract 20.
I can subtract 20. Negative 20 equals negative 16t squared. Now what?
Divide by 16.
Divide by negative
Negative
16.
And
So what is 20 divided by 16? It's 20 divided by 16.
negative 20 times negative 16. That's a big number.
Don't confuse yourself. How many times does 16 go into 20?
1.
And what's left over?
4.
I did.
4.
1 and 1/4.
Yeah, it's 1 and 1/4. But I still haven't solved for t. What else would I have to do?
Divide by t.
What do we call that?
Square root.
Yeah, we find the square root. So the actual time would be the square root of 1.25. Again, you don't have a calculator now, so it's not as important to come up with a solution. But that's how you would use the calculator, or the equation. Sorry. And it would be somewhere in this ballpark, a little bit bigger than 1. Okay, so what we are going to do now, 2 things. Let me pause the video first.